Thank you very much everyone for joining us here for another Guideline Geo webinar. Today we're going to be talking about the vertical electrical sounding method, VES, and as you can see, it's a summary of the method and its uses. So we're going to start pretty low level. We said in the invites and the introduction text to this webinar that it didn't require any geophysical background. So we're going to start with the real basics of a resistivity measurement, and then we'll move on through to how we undertake VES, the typical applications that it might be used for. And then we'll look at some of the software packages that we can use to process data. And then we'll do just a very short example of how data might be collected on an instrument, and also just sort of run through the processing steps in one of those software packages. And that should take us pretty much through the hour that we have allotted for this webinar. So for those who don't know me, my name's Jimmy Adcock. I am the product manager for the ABEM range. That means that I look after the maintenance and development of our seismic, resistivity and TEM instruments. I've been with Guideline Geo for 6 years, and I took over the product manager role last year, having been an applications engineer when I first started. If you're relatively new to Guideline Geo and you've just sort of come in because you're interested in the VES method, I'll do a very short introduction to the company, and I apologize for those who've sat through these webinars before and have seen these slides many times. So Guideline Geo, we are a Swedish manufacturer of geophysical equipment. We have two product ranges. We have the Mahler GPR range, so ground penetrating radar, and the ABEM range, which is the more traditional geophysics. So that's resistivity, seismic, and time domain electromagnetics. Guideline Geo have offices right the way around the globe, so we cover most time zones pretty well. This is a list of our main offices, and they are a combination of sales and technical support, but we also have somewhere between 60 and 80 distributors spread around the globe between these offices. Heart of the company is in Sweden, so our head office is in Stockholm. Our research and development office is in Umeå, somewhat further north, and then right up by the Arctic Circle is actually where our factory is, and that's where we manufacture all of the systems that you might purchase from us. Myself, I'm based in Manchester in the UK, so pleasingly right in the middle of this, this big map. Guideline Geo can kind of trace its roots back a very long way. As our involvement in geophysics can be traced to about 1923, and that's when ABEM was first set up as a company offering prospection services, exploration services for the mineral sector in Sweden using electrical methods. And that gradually morphed from being a service provider into an equipment manufacturer, selling the hardware to do the surveys. Mahler came out of a Swedish geological office that was set up in the town of Mahler around about 1937. And the two companies have kind of developed over the years, and as of 2013, come under the same Guideline Geo banner. So we're here to not talk about the history of the company. We're here to talk about vertical electrical sounding. And I'll be using the Terrameter LS2 for the sort of example measurements that we'll do at the end. And as I said, if you have any questions, please just put them into the chat or the Q&A section. And then when we get to the end of the talk, I'll go through all of the questions in turn and make sure we cover absolutely everything. So I said we're going to start very basic. So that's what these first few slides are going to be. The resistivity method is what we call an active method. So we're not measuring some property of the soil that is always there. We are generating a signal, and we look at how the ground changes that signal to tell us something about the structure beneath us. And so the way that we generate that signal is we inject a current into the ground, and the thing that we're trying to map is the resistance against that flow of current. So things like hard rock very dry rocks will tend to have a very high resistance, and aquifers, you know, where you've got a higher percentage of water, the water conducts the electricity more easily, and therefore we see a lower resistivity. Other things can do that, such as mineral bodies. They can be very conductive in their own right, and so therefore, again, they would display a reduction in the resistance to that flow of current. The principles that we use are some of the most basic principles in physics, and it's to do with how electrical currents flow around a circuit. So the basic principle is that the current flowing in a circuit is related to the driving voltage, so how much power we have in our battery, against the resistance to the flow of current through the circuit. So if you have more resistance, then the current starts going down. If you have more voltage, the current will start going back up again. So there's two circuits here, and they both have the same resistance, total resistance within them, and that resistance is resulting in a flow of 5 milliamps. But what you can see is that on the left-hand side, the resistance is all in one place. It's on this single component. And in the diagram on the right-hand side, the resistance is split between two components, but the current remains the same, provided that the total resistance is the same. So when we're injecting current into the ground, the resistance of the material between the current injector A and the current injector B determines how much current can flow. Now, fortunately, if we measure the voltage within our circuit at any point, we can determine the resistance of the component or the materials that are between the two places where we are recording that voltage, because the voltage varies in the same proportion that the resistance varies. So what we see in our simple diagram on the left-hand side, where all of that resistance is in one place, is that we have a voltage of 1.5 volts, the total voltage supplied by the battery, and we can use Ohm's law to give us the resistance value for that particular component. So Ohm's law just states that the voltage in the circuit is equal to the current flowing multiplied by the resistance. So we can rearrange that. So resistance is the voltage divided by the current, and that allows us to determine, right, that component is 300 ohms. In the diagram on the right-hand side, we can see that the resistance is split in a ratio of 2 to 1, and that the voltage also splits in a ratio of 2 to 1 as well. So when we're talking about surveying in the real world, what we're talking about is measuring voltage at different locations on the ground, and then being able to determine the resistance of the volume of earth that we've just measured. Now, in a laboratory, doing those measurements is really easy. We can just use a simple electrical test meter with two probes. We put the probes on either side of the component that we're interested in, and Ohm's law will give us our resistance by knowing the voltage in the battery and the current flowing through the circuit. For the real world, it's a little bit trickier. We need to use 4 electrodes in the real world. So we have our metal stakes hammered into the ground, and that's what allows us to transfer current from our VES cables into the ground, and also to connect our measurement circuits to a position within the ground near to our current injectors. And so we have the 2 that set up the flow of current through the earth, and then our 2 that are going to measure the voltage. Then, as we've said in all the previous slides, we just use Ohm's law to calculate a resistance, and then we convert that into an apparent resistivity. And we'll talk about what we mean by apparent resistivity in a moment. But ultimately, that is what we take out, take away to process and to develop a model of what the subsurface looks like. Now, all of that happens inside the instrument. So that's nice and easy. There's no complicated maths for us to have to do while we're in the field. The instrument will be doing it for us. Now, this method of using 4 electrodes to determine a resistivity, to measure the electrical properties of the ground, has actually been around for a very long time. And so anyone who's even come close to geophysics will probably have heard of a man called Venner. And he published this note in 1915 called A Method of Measuring Earth Resistivity. And it uses 4-probe method with equally spaced electrodes. And that method still carries his name to this day. So it's been around for a good while. This is not a particularly innovative method of measuring resistivity, but it's one that works and works reliably. The reason why we have to use 4 electrodes is really about the problem of persuading current to flow from the nice conductive cables into the ground beneath us. Now, the ground itself may be relatively conductive, but the point where we need to get the current to jump from the electrode into the ground is the tricky bit. We have what's called contact resistances, and these can be very, very high, especially if you're working on very hard ground or very dry ground. So the contact resistance is going to contribute to that total path resistance. And we said that the path resistance is what is going to determine how much current flows through the ground. If we have a small current flowing, the measured voltage that we get back is going to be very small. And if the measured voltage that we get back to calculate our resistance and convert to apparent resistivity is small, then it's at risk of getting lost within the electrical noise that is all around us, from electromagnetic transmissions like TV, radio, mobile phones, transmissions of the national electrical grid. All sorts of things generate electrical noise in the soils and the rocks beneath us. And so we want to try and ensure that our signals are as big as possible to give us the best possible chance of detecting them. So we really need to try and either cancel out the effect of that contact resistance, that resistance of trying to get the current from the electrode into the ground, or alternatively, find a way to either build the instrument in such a way we cancel it out, or we reduce it when we're in the field. And that's something we'll talk about later in the presentation. So basically, with our 4-probe setup, if we take the Ohm's law of how do we calculate resistance, well, we take the measured voltage, so that's the voltage between our central electrodes, and we divide it by the current flowing between our current electrodes. So that's what we said in the previous slide. And so the resistance that comes back is going to be the sum of a lot of different components of the system. So it's going to be the contact resistance. So that is the resistance at the point where the electrodes meet the ground. So we've got 2 electrodes, so we've got 2 lots of that contact resistance. It'll also be the resistance between the pair that we're measuring the voltage with. So that's this RMN, and that's the one we want. That's the one we're really interested in. That's the one that will allow us to calculate an apparent resistivity for the volume of Earth between those measuring probes. And then also, the design of the measurement instrument means that there will be an internal resistance to the system. Now, what we would really like to be able to do at the point where we take the measurement is to cancel out all of these effects that we've got highlighted in red here. Oops, sorry, all of the effects that are highlighted in red. Because if we can cancel out that part, then that just leaves us with the resistance MN, the resistance between our voltage electrodes, and that's the one we need to calculate our apparent resistivity. So if we actually use some real world numbers for this, and then use the equation that will give us the total resistance of this setup of our system, we can see how effective this might be. So basically, we're going to have a value for the resistance between our measuring probes. That'll be quite small, so that's just going to be 20 ohms. So that's RMN, this value here. That's going to be 20 ohms. Then we want the contact resistance on each of our electrodes, and let's be quite kind. Let's say it's just 1,000 ohms, so not too big. So 1,000 ohms. And then we're going to say that the input resistance, that's the internal resistance of our measuring meter, is going to be 200 mega ohms. So that's 200 million ohms. So here's the equation that calculates all that. If we calculate the first part of the equation, that is the path resistance multiplied by the resistance of the meter, we end up with a value of 4 billion ohms. Ridiculously large number, but don't worry, we're going to resolve this. If we then look at the bottom half of the equation, which is 2 times our contact resistance, so that's 2000 ohms, plus our input resistance, which is 2 million ohms, plus the bit we're interested in, the RMN, the resistance between those measuring electrodes of 20, we end up with 2,002,020 ohms. And then if we use both to finalize the calculation, we end up with that big number divided by this quite big number, and the end result is 19.99979 ohms. And that is pretty much that path resistance that we were interested in, that bit of ground, that volume of ground between our measuring electrodes. And so what we've managed to do is we've managed to counteract that contact resistance. And the only reason we've been able to do that is that we have a very, very large resistance inside the meter. So when you look at the design of a resistivity meter, the bigger this number is, the more, the better you can counteract the contact resistance, and the closer you'll be able to get to measuring the true resistance between those voltage probes. So we have, the only ways that we can affect that is to use an instrument with a very high internal resistance, called an impedance. But we can't really change that. That's usually hardwired into the design of the instrument. So what we can do is we can always work to reduce the contact resistances. And again, that's something we're going to talk about when we talk about the QA, the quality assessment of our data. How can we ensure we're collecting good data, give ourselves the best chance of coming back to the office with a usable data set? So that's the kind of theory, but I've been throwing around a few terms there: resistance, apparent resistivity, and resistivity. So let's just double check we're all using those terms in the same way. Resistance is the kind of raw value that we calculate. We calculate that using Ohm's law from the voltage measured and the current flowing. And the problem with resistance, the reason why we can't just use resistance on its own, is that it varies depending upon how much material you have. So if you imagine having a copper wire, if you lengthen that copper wire, the resistance that you would measure from one end to the other would increase. But if you made that copper wire thicker, there's more space for the current to flow through it, and the resistance would reduce. So just by changing the volume of material and the shape of material that we're dealing with, we can change the resistance, even though the material itself hasn't actually changed. We've just changed the size or the shape of it. So what we really want is something that is fixed to a particular material, and that's resistivity. So resistivity is an inherent property of a particular material. And so a way to think about it is like the similarities between the weight of something and the density of something. So I have my nice Guideline Geo water bottle, and there's a certain amount of water in there. And if I weigh it, it weighs a certain amount. If I drink some of it, the water inside there now weighs less, but the density of the water hasn't changed. So the density of that is completely irrespective of how much of it I have. And that's why we want to use resistivity. Doesn't matter how much of the material we're measuring, the resistivity is the same, but the resistance could change depending on where the electrodes are. So resistivity is not given in ohms like resistance, given in ohm meters. And that meter gives you an impression that actually this is dealing with more than just a single simple measurement. This is dealing with a volume. But we talk a lot about apparent resistivity, and that's the raw data that we take off the instrument. And the reason that it's called apparent resistivity is that we are taking our measurements from the surface. And that means that our current paths are flowing through the whole of that ground beneath our feet. And so all of the different layers that we're trying to detect are going to have an influence upon the values that we measure. So it's only apparent resistivity at this stage. And what we need to do in the processing is find a way to convert from apparent resistivity, the measurement of the surface, to the true resistivity of each of the individual layers that we can't measure directly. The way that we get to apparent resistivity is we take the measured resistance, which is just taking the voltage that our instrument records and dividing it by the current that was flowing. That gives us resistance value. We then multiply that by what's called a geometric factor. That's given the letter K. So K factor or geometric factor, that works out how big a volume that current has flowed through, and that allows us to convert to apparent resistivity. And so it's a way of normalizing our measurements. So for a given focus position, for a given point in the ground that our electrodes are sensitive to, if we change the order of the electrodes, we'll get a different resistance value. But if we multiply it by its geometric factor for that arrangement of electrodes, we'll get the same apparent resistivity back for a given point in the ground. So it allows us to normalize between different measurement types. Now, once we've calculated our resistivity, then we can start doing our interpretation. And our interpretation can be one of two things. It could be an absolute interpretation where we look at the resistivity, which increases across the top of this diagram, and find the value that's been returned, and then look at what potential materials could cause that resistivity and say, right, we think this layer is potentially dry, gravel, and sand. Alternatively, we can do a relative interpretation where we understand the geology of the region that we're working in, we understand what the likely resistivity should be, and then we look for where the resistivity changes away from that known value. And that could be because of something included within the geology. For example, water, which is going to draw the resistivity lower, or some kind of mineral inclusion, which again would draw the resistivity lower, or it might be a void. A void full of air is a perfect insulator. It doesn't allow current to pass through it, and therefore we would see the resistivity in that region increase. So absolute or relative interpretations, or more likely, a combination of the two. There are some limitations to the resistivity method, and it's only fair that we kind of talk about those as well. And probably the biggest one is the fact that current is quite lazy. It will always take the path of least resistance. So if we have a very conductive top layer, the majority of the current will be flowing in that top layer, and that means that it will be much smaller currents in the layers beneath. And then what did we say about having smaller current? We said that means that we'll get a smaller returned signal, and therefore that returned signal may be less stable, may be more prone to interference. So if we have something very conductive at the surface, it will be difficult for us. That effect remains even if we spread our electrodes further apart and try and force the current deeper in the ground, or even if we turn the power up and actually put more current in. What happens is that the majority of it still stays in that top surface. Another limitation is the fact that we have to have a physical electrical connection. We call that a galvanic connection. So we need to have these metal probes in contact with the ground. And that can be problematic if we have a very dry top surface, which is highly resistive, or if we've got exposed bedrock. So if we have exposed bedrock, then our choices are to either use a different method, something a bit like TEM, or to drill our electrodes in, or alternatively, a bit simpler than drilling, use plate electrodes. So rather than a metal stake, we have a flat electrode with our cable attached to it. We place that on the bedrock and normally put some kind of conductive material, either clay or gel, between the plate and the bedrock. And what are we doing there? Well, we're increasing the surface area, which makes it easier for the current to pass between that plate and the geology. And then those of you who are kind of eagle-eyed or very long in the tooth when it comes to geophysics will know that many materials have very similar resistivity. So we see here that the range of resistivities for a lot of these geological materials and different types of water are very, very similar. And so that makes it difficult for us to interpret. And what we say is that it's rare that any one geophysical method will give you the absolute answer. We normally need to combine it with another data stream. Now, the simplest data stream to combine it with is your own knowledge and common sense. So you should know something about the geology of the area that you're working in, and that allows you to discount some of these materials. But that can still leave us with issues if we're looking for fresh water and we're also in a region where there are likely to be clay deposits. We can see that the resistivity of clay and fresh water overlap almost entirely. And so therefore it can be very difficult for us to tell whether we have a clay layer or a perched freshwater table. So that's just generic sort of resistivity theory, just to bring us all up to speed. So now let's talk about the particulars of the VES method. So vertical electrical sounding. Sounding means that we are collecting data in a single vertical line directly beneath our feet. It's kind of the physics equivalent of drilling. We don't change our X and Y location during a single measurement. It's simply depth that's changing, and we're looking at the resistivities at the different levels. Because it's a 1D method, we're not looking out to the sides, simply looking straight down. This method is best suited to large targets which have a relatively flat top, because we have no way of determining how far that target extends beyond our single measurement point. And it's very difficult for us to tell whether it is dipping or whether it's horizontal, again, from a single sounding. Advantages of VES are that it's a very easy method to get into. The hardware is relatively low cost compared to a lot of other geophysical methods, because a resistivity meter can be quite simple. You only need 4 electrodes. You have 4 single core cables, one attached to each of the individual probes. Field procedure also is very quick to learn. It's very simple to teach someone how to collect VES data. You are simply moving those electrodes further and further apart to gradually measure deeper. The downside is it is only one-dimensional data. It's a single 1D sounding. So we have to make big assumptions about what happens beyond our measurement area. So what we say is that for a VES sounding to be accurate, we need to have layers that are homogeneous, i.e. the resistivity doesn't change within those layers, that they are horizontal, so one layer on top of another, not dipping in any direction, and that those same layers extend in all directions to the horizon. Now, in reality, that isn't going to happen very often, so we have to be aware when we do our interpretation, if we only have a single sounding, that there could be complications lying beyond where we've taken that measurement from. So we'll talk about ways in which we can try and ascertain, try and determine whether or not we are meeting those assumptions correctly within the environment that we're working later in the presentation. Applications. The traditional applications for VES are water search and mineral search. So we're not talking about mapping in detail. What we're talking about is getting out into a large landscape, doing a series of 1D soundings and trying to find hotspots where the resistivity values are indicating that there may be a deposit of water or there may be a mineral deposit, which we can then come back and investigate in more detail with another method. Perhaps it's going to be ERT, perhaps it's going to be an electromagnetic method, perhaps it's just going to be drilling. But ultimately with VES, we're tending to do search type surveys rather than detailed mapping. There is a strong overlap in applications between VES and TEM. You find that they're both used for water and minerals. They both produce a 1D sounding. The obvious advantage of TEM is that that is a method that doesn't require this physical electrical connection. It uses wire loops to induce a signal into the ground and then receive the responses that come back. So it's very good if you have these, bare rock at the surface. It can also deal relatively well with conductive top layers, because with TEM, it's actually a bit easier for us to apply more energy, put more power into the transmitted signal to try and break through that conductive top surface. So the field procedure for VES, what do we do when we take the measurements? Well, we set our instrument up, and in this particular diagram, you can see that we have a sort of icon of a Terrameter LS or an LS2, and we would have 4 electrodes. So 2 current electrodes on the outside, they're labeled A and B in the textbooks, and then 2 voltage pairs, a voltage pair in the middle, M and N, that are measuring our return signal. And for a given arrangement of electrodes, we will have what's called a focus position. And that's where we say the ground is making the biggest contribution to the signal that we receive. So we say the apparent resistivity that we have measured is focused on that red cross. So I take a measurement there, then I spread A and B further apart, and that forces the current deeper into the ground. So my focus position moves down. And then I repeat that process over and over again, gradually building up this 1D picture of apparent resistivity against depth. So what I'll see on the instrument, what I see on the instrument for that is what we call a sounding curve. So you have apparent resistivity from left to right, and we have depth increasing down the left-hand side. So that's our raw data. We then take that raw data, that sounding curve, off the instrument, put it into inversion software, and we let the inversion software then process the data and return to us, hopefully, an accurate model of the subsurface that shows us layer thicknesses and resistivity. So again, we've got depth down the side, but this time it's true resistivity, or at least we hope it's true resistivity, across the bottom. So here we see resistivity near surface, then dropping, then increasing, and then staying fairly consistent as it gets deeper. So how does this inversion software work? Well, we provide it with the raw data. So we provide it with our sounding curve of apparent resistivity against depth. The inversion software then generates a model of what it thinks the ground looks like. So it will be a certain number of layers with resistivities associated with those different layers. It then repeats the survey process that we undertook in the real world on that model. And it looks at what the data would have looked like if the ground was the same as our model. So here you see that the model data doesn't fit with the inverted data, with our raw data. So the inversion software changes the model and tries again. And it keeps changing the model until it gets somewhere close to a good fit between the modeled data and our true data from the field. And when it's done that, it presents us with synthetic model, in this instance, number 4, and presents us with also a residual. The residual tells us how closely the curve from the model fits the curve from the real world. And so theoretically, the lower the percentage that we get back, or the numeric value that we get back, the closer the two curves are to each other. So theoretically, lower is better, but there is one caveat. There's one thing we need to remember. Lower is only better if the model that we get is geologically realistic. So we need to know something about the geology of the site that we're on to know that this model is truly what we were working above. Different models could produce similar curves. So if you have a very thin, highly resistive layer, it can be very similar to a much thicker, lower resistivity layer at a roughly the same depth. So we need to think about, is the model that it's presenting me what I would expect within this geological environment? So again, that secondary data stream is helping us with our interpretation. Another thing that we can do is we can also collect chargeability data. So we can look at how the ground charges up when the current is switched on and discharges when the current is switched off. So this is something that can be very useful, especially in water and mineral surveys, this IP effect, induced polarization effect. So we switch the current on, the ground charges up, the voltage builds up. We then measure that voltage to get our apparent resistivity value. If we then switch the current off, the voltage will not disappear immediately, but will decay over time. And if that decay is very slow, that tells us that the ground is holding the voltage. The ground has a high chargeability. So what it looks like on an instrument is we switch the current on, we wait for the voltage to stabilize, so we have a little delay period, and then we measure the voltage over a certain period of time. We average it to improve the quality of the data, and that is used to calculate resistance and convert to apparent resistivity. Then we switch the current off, and then the voltage in the ground drops away slowly over time, and that then gives us our IP effect, our chargeability. We then repeat the process in the opposite direction, so we reverse the direction of the current, take another resistivity measurement, then switch it off and measure our IP effect again. And we switch the direction of the current within a single measurement cycle to avoid any kind of bias, any drift. We don't want the current always flowing in the same direction. We would end up biasing the voltage that we measure at the end. So we go both forwards and backwards, and then hopefully by the end of the measurement, the ground is in the same electrical state that it started in. So why do we want to measure the IP effect and determine the chargeability? Well, some materials have a high chargeability associated with them. So big sulfide mineral bodies do. Clay deposits, anything with a lot of clay minerals in it will have high IP, high chargeability. And graphite also has a distinct IP effect, a high chargeability associated with it. But we can also just use it as a secondary data set to aid our interpretation. So if we remember the resistivity model, the resistivity table that we looked at before with different geological materials and resistivity increasing from left to right, there was lots of overlap. But if we input the chargeability values for different materials, we can actually see that that would help us to start separating out between those materials with similar resistivity. And one of the big ones here is that clay and fresh water confusion. The clay will have a much, much higher chargeability associated with it than fresh water. There is a downside to IP, and that was that traditionally it was quite a slow method because all of our measurement cycles had to have these off periods, and the current needed to be switched off for at least as long as the current was switched on. So in a normal resistivity measurement, we don't switch the current off at all. We just swap it from positive to negative, forwards and backwards all the time. So much, much faster to just collect resistivity data. IP could take longer time. On the LS2, we've introduced what's called the 100% duty cycle for measuring that IP effect. And in doing so, we don't switch the current off. What we do is we measure the IP effect at the point where the current switches from being positive polarity to negative polarity, where it changes direction. So we look at how the voltage drops and then switches polarity and increases in that opposite polarity. And the advantage that that gives us is, firstly, we have a bigger IP effect because we're not measuring from just positive to zero or from negative to zero. We're measuring all the way from positive through to negative and then negative through to positive. Much bigger effect for us to see. And also it's much faster because we don't have an off period, which means that we can repeat the measurement more often. And the IP effect, these changes that we're looking for are very, very subtle, very small. And so anything that we can do to improve the signal to noise ratio, which we do when we repeat a measurement and then average the result, anything we can do to improve that signal to noise ratio will give us a better data set at the end of the day. And if you're interested in that 100% duty cycle, what the impact it has on your IP measurements, then we actually did a webinar a couple of weeks ago on that, and you can find that on our Guideline Geo YouTube page. So go and have a look at that. So a typical layout for a VES configuration is our resistivity meter at the center. And so for ABEM, that would be either our SAS 1000 instrument or our Terrameter LS or Terrameter LS2. We would have 4 cable drums with single strand cable on each that attach to our 4 electrodes. So there are 2 very long cable drums for the outside electrodes, the current electrodes, 2 shorter cable drums that we use for measuring the voltage at the center. We can then decide whether we use what's called a Venner measurement, we talked about him earlier, or a Schlumberger measurement. They are both excellent for finding horizontal interfaces, so horizontal layers. And we said already that for a 1D measurement, those are our best targets. So these Venner and Schlumberger arrays, they will define the contact between separate layers much more closely than some of the other arrays that are available. And then our choice is whether we want Venner or Schlumberger. Venner has a better signal to noise ratio. If you're going very deep, Venner would give you the best chance of getting reliable results at the deepest levels. But the downside is, for a Venner measurement, all of our electrodes need to be equally spaced. So every time we take a measurement, we have to move all 4 electrodes. If we choose the Schlumberger, we don't have quite the same signal strength, but we have the advantage that most of the time we only need to move the outside electrodes, the ones that are injecting current. So if we have a look at what that would look like for a number of readings, this would be our first Venner measurement, then our second, third, fourth, and fifth. And what you see is that all 4 electrodes are being moved every time we want to take a new measurement. If we look at Schlumberger, you can see that for these first 1, 2, 3, 4, 5 measurements, only the current electrodes are being moved further and further apart to get deeper and deeper readings. The voltage pair in the middle don't change. Now, the effect that has is that as the current electrodes get further away from the potential electrodes, from the voltage electrodes, the signal gets weaker. So at some point, we want to counteract that. We want to improve the signal strength. And we do that by then broadening out that central pair. So after, in this instance, 5 measurements, we widen the central pair, and that increases the voltage that we measure and increases, i.e., the signal strength. But that gives us a little problem as well, because that means that for the same current spacing, current electrode spacing, which is giving us a focus point at a particular depth, we've now got 2 different voltage measurements. So when we come to do the processing, we need to normalize those. We need to bring the second set of data with the new position for the voltage electrodes up to meet our original data set. And so we make sure that we repeat this reading. So you see the same current pair is repeated so that we can compare the difference between the 2 sets of data. And if we want to do it properly, we actually overlap by 2 or 3 readings. So we actually take a step back with our current injectors, take this measurement again, but with the new voltage pair. And that allows us to then be able to adjust to account for the fact that the signal steps up at the point where we change the spacing at the center. So what can we do to ensure that we're collecting good data while we're in the field? Well, there's a number of things. First thing we can do is we can take what we call reciprocal measurements. So this is very easy for a VES survey because we only have 4 electrodes. With a reciprocal measurement, we are swapping the position of the current injectors and the voltage measurement pair. So whereas before we had C1 and C2 on the outside and our potential pair in the middle, we then put the potential pair on the outside and the current injectors in the middle. Now, that's going to give us a different resistance, but that arrangement of electrodes has a different volume factor, a different K number. So when we multiply that different resistance by the K factor, we should end up with the same apparent resistivity. If we don't, that suggests that the assumptions that we make for a 1D sounding, i.e. that the layers are horizontal, homogeneous, and extend in all directions without changing, one of those or more of those are not being met. So we know that maybe 1D soundings are not going to work well in this environment. And we can actually put a quantitative assessment of that by using this equation and comparing mathematically the normal and reciprocal measurements. Really easy with VES. You have your layout, you take a measurement in the normal configuration, you then take the connectors out the end panel of the instrument, put them into their opposite compatriate, and then repeat the measurement for that reciprocal arrangement and see what the value you get returned is. So very, very simple, real quick way to see if those assumptions are being met. Another option is cross lines. So this is where we again test whether the assumption we've made about the geology not changing around our survey area is true. So we take our first measurement, our first VES sounding, and then we repeat it with the line of electrodes spreading out in a different direction. Commonly at 90 degrees, but it doesn't have to be, whatever works in the landscape that you're working. So if you do these cross lines and then compare the models that you get back, if they're significantly different, that tells us that something isn't quite right in terms of the assumptions that we have to make for a 1D sounding. And so perhaps in that particular environment, a 2D measurement, ERT imaging, would be better. So that's telling us whether the geology meets our assumptions. Then we want to talk about the inherent quality of the data. And so for this, we would look at the error limits on the instrumentation themselves. So when you take a measurement, the instrument should tell you how stable the received signal, the measured voltage, is during the measurement cycle. And so on the Terrameter LS, it will show us a standard deviation, but it'll tell us how much the voltage has varied up and down during the cycle. If you've got good quality data, it shouldn't be varying. We should have a very, very small standard deviation. If it's bigger, then we need to look at the settings that we've used, make sure that we're using good settings for the environment that we're working in, and then double check our electrodes. Do we need to improve the contact resistance on those electrodes so that we can get more current into the ground? And the final thing is a really simple one. It's the battery voltage. We rely upon some kind of power supply when we're out in the field. And if that battery voltage doesn't hold up well during the measurement cycle, the transmitter is going to struggle to put a good stable signal into the ground. If we don't have a good stable signal going in, we're not going to get a nice stable signal coming out. So the voltage that we measure is not going to be stable. So always make sure we've got good quality batteries and that they're in a good state of charge. So that's all while we're in the field. That's what we can do whilst we're collecting data. I had a look on our support system to look at why people have issues when they send us data that perhaps has high standard deviations or lots of negative values. And I can trace the source of the problems normally back to one of three things. And that is the position of the electrode and the material immediately surrounding those electrodes, the power supply, i.e. the battery, or the settings that have been used for the measurement. So if we talk about electrode placement, it's normally that you've got very stony ground. So there isn't sort of a good, the ground isn't hugging the electrode, providing good contact resistance. You've got lots of gaps between the stones. That has air in it. The air doesn't transmit current, and that's increasing our contact resistance. Could be similar if you have like a sandy soil, you push the electrode in, and unless you're very careful, it might tend to push sideways and leave an air gap on one side of the electrode, reducing the area that is in contact with the ground and therefore increasing the contact resistance again. And then also just very dry or very resistive ground, perhaps bare rock, where again, the contact resistances are high, and if they're high, the current going in is much lower. So we can do stuff about that. We can water our probes, hammer our probes in deeper. We can use some kind of conductive material like clay or electrolyte gel to reduce the contact resistance, or we can increase the surface area by using plate electrodes or using more than one electrode connected to the input on the instrument. So if we connect a number of electrodes together, they act as one bigger electrode. It increases the surface area and therefore allows the current to flow into the ground more easily with a lower resistance. Power supply, it's one of three things. It will be an undercharged battery, a battery that just doesn't have enough power to be able to last for a day's survey, or it's a depleted battery. And the last one can be a problem because you can have a battery where the internal cells, the things that hold the electrical charge, the energy, have started to break down. You charge it up and your charger says, oh, this battery is full now. And you put a simple test meter on it and it says, yeah, there's 12 point something volts in it. But as soon as you put a load on it, as soon as you try to draw current from it, that voltage collapses. And when the voltage in the battery collapses, the transmitter will struggle to inject current. So for example, during the injection of current, if you're in a very resistive environment or you're particularly conductive environment and you've got very high settings, So either you're using very high current or you've got a very high voltage trying to push the current in. The instrument could be drawing anything up to 30 amps from that battery. So if that battery isn't healthy, it will very quickly show the pain. And then the final one is transmitter settings. Make sure that you have got settings appropriate to the environment that you're working in. So don't set them too low. That will cause a small signal to be put in. And as we said, then likely a poor signal coming out. But also if you're in more conductive environments, don't set it too high, because what will happen is you'll draw your external battery down very rapidly. And then that might compromise the transmitter later in the survey where you're trying to take the deepest measurements where you want the best possible data quality. So that's all about kind of field work so far. We've done theory, field work. Let's just talk a little bit about processing the data. So I thought I'd just talk about the software that I've experienced during my time in Guideline Geo. And there have been 3 software options really that we've used. The first is called Interprix IX1D. So that is just for inverting the raw soundings. SPEAR DC, again, just for inverting the soundings. And then using SPEAR DC with a piece of software called Workbench. And these 2 come from Aarhus Geo software. And Workbench allows you to do a little bit more with the soundings. So Interprix, we get to see our soundings in relation to each other. So we get to see like a top-down view of where they're all positioned, but it's just in white space. However, we can edit our data, we can invert our data, we can change the model. So that all, everything that we would expect from inversion software. It also allows us to draw a line through our sounding locations and generate a 2D profile. It's not particularly complex in the way that it does it. It kind of just interpolates between them. So you don't get sort of the most advanced 2D profile you could possibly get from 1D soundings, but it gives you an idea of how the geology might change from one location to the other. And it'll also process both resistivity and IP data. SPEAR DC. This has a much more modern interface. It works with tabs. It looks a bit more like sort of a Microsoft sort of environment. It allows us to see all of our soundings on a base map. It again allows us to edit before we do the inversion. It will invert both resistivity and IP. And it does a more advanced inversion of the IP because it doesn't just look at the chargeability, it looks at the shape of the decay. And that can give us some extra parameters to help us with our interpretation. So much more advanced handling of IP than Interprix. But same thing, we can edit the model to try and get a better fit at the end of as our end result. And we've got like a single button press PDF report. So we can take our sounding, press a button, we get a 1-pager PDF that shows us our sounding plus our model plus header information about how and where that data were collected, which can be really useful for putting in appendices of reports or firing out to customers. If we then also add in Workbench, well, then we can take our soundings that we've processed in SPEAR and we can place them into the map in Workbench. And then we can actually do 2D profiles that do what's called a spatially constrained inversion or a laterally constrained inversion that allows us to build a block of data from those 1D soundings, which is better than just interpolating between them. We can also look at our data in 3D space, so we can get an idea of where layers are and how they change across the landscape. And we can also combine other data streams, so other geophysics data, topographic data. We can put in borehole information so that we get a more complete overview of the site we're working in and hopefully a better interpretation at the end of it. So that's kind of the theory, a quick look at some software. Just to finish off, 5 minutes, let's have a look at a measurement on the instrument. So I have behind me an LS, which then has instruments, that then has cables running out into my garden outside the office. And I'm going to remotely connect to that Terrameter. So VNC. So I'm connecting to it via its Wi-Fi network. And so by connecting through just using this VNC server, so this is a remote desktop software, it's free software. I can see the instrument in front of me. I can see all of the menus and I can control the instrument. So what am I going to do? Well, I'm just going to go to my list of projects. I'm going to create a new project. And then that will automatically take me to the task page. So a task is just a measurement. So I want to create a new measurement. And it's already set up. So what I do is I just tell the instrument what type of measurement I want to take and what cables I've got attached. So in this instance, I have a set of VES cables attached that are going to use C1, C2, P1, P2, 4 connectors on the end panel. And then I choose which type of VES measurement I want to take. And I'm going to choose a Schlumberger measurement. Say OK. That will then automatically take me to the settings pages. And we said, we want to kind of use some middle ground settings, not too high, not too low. Unfortunately, to help you with that, we have the option to just load in some settings that will work in kind of 75, 80% of occasions. So we can load those in, and they are IP, resistivity, or 100% duty cycle measurements. So I've already got those settings loaded in for this measurement. So I'm going to jump to the data collection screen. And what we see is that the instrument is telling me where to position my electrodes. So there is a list of preloaded positions, electrode positions for a Schlumberger arrangement. And these are based on the kind of theoretical resolution decreasing as you get deeper and deeper. So it's kind of like an ideal set of electrode spacings. But you can actually generate your own file. You can generate your own VES file that you load onto the instrument, and then your preferred set of MN and AB spacings will be loaded into this list for you to use. So if I then jump back to the measurement screen, so I can just use the left and right arrow to then jump through the different measurement choices. So I'll start with the first one, and I just say start measuring. So it warns me to make sure no one is touching the electrodes. So it's saying preparing to measure. It's going to do an electrode test, first of all, to make sure that it can inject a decent amount of current through the electrodes. And what we see is that the electrode test has failed. So that tells me that one of my electrodes isn't connected. And I will guarantee that someone has tripped over the wire that is outside. So let's have a look. Let's see what the results page says. Oh no, it's just that I've got a slightly high contact resistance on one of my electrodes. So I'm just going to change my settings so I don't have to go out and actually water the electrode to try and improve the contact resistance. Let's just change the threshold on my electrode test. Jump back to my measurement screen, say start measuring. So we'll do the electrode test again. This time I've set the threshold, the kind of contact resistance that I will accept, set that a bit higher. And now it's taking the measurement. So we can see down here, it's measuring, showing me on screen the last measurement that was made, but this will update with the new values in a moment. There we go. So I've got, at the current electrodes, an input of 5 milliamps. It's just in my garden, so the electrodes are really close. So it's not using much power. 25 volts, pushing that current through. The current didn't change on the input signal. So this is telling you the standard deviation of the input current. And you can see it's 0.2 parts per thousand. So these aren't per cent, these are per mil, because there's an extra 0 on the icon. So hardly changed at all. And then on the potential pair, the voltage measurement is returned 248 millivolts. And that again hasn't really changed very much. It's 2 parts per 1,000 during the measurement process. So I'm quite happy with that. I'm happy that I've got good quality data coming in. So I'm going to jump back to my measurement screen. I would shift my electrodes in the field and then take the next measurement. So up to the next choice, say start measuring. It will go through the same process again. It will test the resistance on the electrodes, make sure that it can inject current through the current injectors, and then do the measurement. So this will now do the resistivity measurement, and what we'll see are these values will update once it's completed the cycle. And this is using the traditional IP method, so the slower method. So to change those values that we've got, and what you'll see is that the voltage hasn't actually changed because the electrodes haven't moved, but because it thinks the spacing is different, I now have a different apparent resistivity. If I jump along to my results tab, my sounding curve, we can see that the first 2 data points have appeared. If I look at a data set that I've actually collected more data within, project list, and go down to this VES one at the bottom, load that in, and then have a look at the sounding curve for this one. It's wrong button, sorry. Bring up the menu, jump to the VES curve. Here we can see that there are more data points in this particular sounding. And what it's done is you've got 3 sections. So each of those sections is a separate MN spacing, and we've changed the icon to indicate that MN has changed between these individual sections. So once I've completed my VES, I can then go into my software. So LS Toolbox, that's the free companion software that comes with the LS. Again, connect to the instrument via the Wi-Fi. Manage project. So I'm just going to download the data in that VES folder. And that's going to import it. Now, I could just import a table of values from the instrument, the averaged values, which are basically which electrodes are being used, injected current, injected voltage, and then also the voltages returned and the resistance and apparent resistivity. And that would download in a split second. But what I've downloaded here is what we call the full waveform. So that gives me this extra level of data. So in here, I have table of results. So I've got time and date, electrode positions in the middle here. I've got the focus depth. I've got the current injected, the voltage pushing that current, the measured voltage, the resistance, which is calculation of voltage and current using Ohm's law, the variability, how much did it change during the measurement cycle, and then an apparent resistivity. Towards the end, I've also got the IP data, and then some instrument information. So I've got the latitude and longitude of the instrument. I've also got the internal battery and external battery voltages, and I've got the internal temperature of the instrument. If I was to look at the full waveform, I can then see everything that the instrument did. So this is for the first measurement. You can see the shape of the injected current. So current on in the opposite direction, then current off. And we can see that the voltage pushing that current was changing to maintain a fixed current. Then if I look at what I measured, I still see the current cycle, but I can see how the ground voltage changed. And so I can see that there is a slight IP effect, but very, very small during that off period. And this full waveform is really useful for us for sort of troubleshooting, trying to understand how much noise is in the environment that we're working in, and just being sure that the instrument is working correctly during those measurement cycles. So I can then export the data to a text file from my table. So I can just say export, take that out as a text file, and then that would allow me to process the data. So if I open up Sphere now, final couple of minutes. Also open the text file. So here's the data that I have exported. So I'm going to create a new project and put that into the VES webinar folder. Call that VES. It'll ask me to put the values in. So just jump to my Excel sheet, copy those, paste them in. Then take my AB values, copy those in, and then bring in my apparent resistivity values, copy those in, and then I can see my 3 sections in there, so that's great. So I'm just going to say import. Oh, I have to give the VES node name. So this was Schlum1. Import. And then in my data view, if I click on the measurement sounding, what I see is 4 different data streams. So I've got, if I switch the others off, AB equals, A spacing, the MN spacing difference between the voltage pair of 0.4, so data points associated with that. Data points associated with a spacing of 2 meters, and data points associated with a spacing of 10 meters. And then I can look at all of those together. And I can also look at the combined curve. So the software has automatically made those into a single curve for me, done the correction. So that's fantastic. I could also, if I wanted to, import the position of these data. And I know that was about 315 meters above sea level. And then I can look at this on a map. Now it's opened on a different screen, but that'll tell me where that particular sounding was, just outside of Manchester. And then I can go and run the inversion. If I wanted to, before I run the inversion, I can actually take out data points if I don't trust them. So I can say not in use. So that won't be taken forward for inversion. And then I can just say run. And this will then produce me a model of resistivity against depth and give me a residual, which in this case is a value of 0.36, and also show me a depth of investigation. So that green line tells me where the model stops being reliable. And that is based on the conductivity of the material above and the signal strength that we've got. So basically, if I've got very conductive layers, the reliability of the bottom of the model is not going to be so good. And so this depth of investigation would probably pull up further. This is a very simple site that I was working on where we actually have a very dry baked layer just at the top. So that's this sort of highly resistive part. Then it drops into sort of a relatively damp material, then into something a bit wetter, and then really the geology doesn't change after that until we get well beyond where our DOI is in this particular model. As I said, I can actually then export these, so I can export the model. So pick which one I want to export, say model PDF report, sorry, select it, say model PDF report, save that into my folder, and then I get this result where I've got the sounding curve, the model broken down into a table, and header information about the result. And then I'll also be able to export these as individual images, this as an image, this also as an Excel sheet, just a simple CSV file, which then would allow me to import it into other stuff. So there we go. That's a really quick run through of how we would do a measurement and how we would process it. And maybe we'll do a longer webinar on actual processing at a later date. So thank you very much. I'm going to have a quick look through the questions that came in whilst I was talking.